Okay, guys. Okay, thanks for showing up. I guess we should have these underwater phones that people, when they're swimming, they can still hear lectures. That would be a nice thing. I don't blame you. I'm really happy you guys were able to show up, but I don't blame people who couldn't show up because 3 o'clock in the afternoon is hard enough without the ocean outside, and with the ocean, my God, what hope is there? Anyway. So we are going to do the third and last lecture of LLMs and LRMs for planning and reasoning tasks. So there are again the slides as usual, the same, you know the drill. The slides are available there. Will also be again. I'll show the again the QR code in the next slide too. And then I also posted the audio for the morning's one, and I'm doing the same thing again on recording this audio. But anyway, interested. So in lecture 1 we get the big picture. Lecture 2 actually I wound up doing not just the standard LLM and their limitations, but we also actually did part of the LLM modular, which is can be thought of as a test time scaling technique. And in lecture 3 actually we start from there, and then we talk about post-training, especially this trajectory-based post-training that has become popular, I think probably with O1, but we have no idea what O1 does, and we do know what DeepSeek R1 does, and that's what it does that. And so I'll talk about that, and I'll talk about some interesting issues, so this stuff is like really at the edge right now because these things are happening as we speak. Most of the stuff here has been happening as we speak because, as I told you, half the time when I was in my room, I was talking to reporters about the Apple stuff, which repeats whatever we did, and so and then sometimes we go to the ocean. But anyway, but this stuff is really more about trying to understand what the post-training methods are doing, and what are the misconceptions around it too. That's the thing, and so I'll get there. And then again, this is again the same slides. But if you have any questions, about anything that we discussed up until now, feel free to ask. Of course, you can ask me afterwards too. Two things that came out in long discussions after the morning session that I thought might be of interest to other people too is, in general in LLMs, the training data effects are not well understood. You have no idea what is in the training data, and sometimes the answers to the questions might actually be in the training data, and you really don't know for sure. And to some extent, even when there are open models, the open models provide open weights. They don't show the data on which they've been trained, and that winds up actually being important to do a methodological, a systematic evaluation of are you guessing or are you actually reasoning. Olmo is from AI2, that's the only exception to the rule, that they actually provide the data on which they're trained on, but it's a smaller model, it's not one of the, and commercial ones obviously don't, and for DeepSeek R1 also doesn't give the data. The second thing that, one of the things that some people are asking is, in the LLM modulo thing, right, so we have this bank of verifiers. So the question is, how important is that these verifiers are both sound and complete? And I think I tried to make it clear that essentially this will be, first of all, variety of verifiers, some of them classical ones, and they may just be sound and not necessarily complete. And so the soundness is kind of more important, that if it actually says the solution is good, then maybe you can actually go ahead and execute it. But we allow these verifiers even to be, definitely to be not complete, in the sense that if there is a solution that actually is a solution but they don't verify it to be a solution, that's okay, you will just continue going back, okay? And furthermore, partial verifiers are also allowed, essentially because in the case of code generation, in the software code generation sort of a thing, what you have is unit tests. And with the unit tests, all you know is that if a piece of code passes the, fails the unit test, it definitely is bad code. But if it passes, it may still be bad code because there may be some unit tests that you haven't written and so it's missing some edge cases. right? So in some sense, it's our partial verification. Yes.
Ask a question about the PlanBench code and in particular the conversion from the natural language response and the input to the model checkers, because that could be the bottleneck. Because if the translation is not accurate, you may prove that everything is fine while it's not.
Yeah, so the point, of course, in general, yes, the question of translation. So your worry is that a bad plan came and then you convert it in translation, you convert it to the right version and then these things are described. That sort of a possibility exists, but you can also have the opposite possibility that when you can, in general, it doesn't have to be. First of all, one of the things that there is this reformatter, and the reformatter basically every verifier might well be taking a different representation of the partial solution. So this happens in planning all the time. You might have a plan that some critics might be looking at it from the point of view of causal links and the correctness with respect to causal links. Some might be looking at it from the timelines and whether or not all the temporal constraints are satisfied. And so to some extent, one of the points is that the reformatters basically take what is there in the main solution blackboard and convert it into their representation. And there can be errors there. There's nothing with LLMs is guaranteed to some extent, but all of this is sort of at least avoiding some of the obvious problems so that you can actually improve the robustness. Okay. So by the way, the paper, ICMR 2024 paper actually talks a lot about how many different roles LLMs play. In addition to this being an LLM, which is basically guessing the solution, you can use LLMs to do reformatting too. In fact, that's one of the things that LLMs have created. They convert format from one format to another format, almost by just at the prompt level. And similarly, you can improve the problem specification as well as domain model generation again with the LLM. So there are multiple roles large language models can play in this kind of an architecture. Anyway, so that's a couple of questions that came up and I just want to mention. So I did mention in the morning that in trying to go from standard LLMs, which is basically GPT-4 and before, to the reasoning, quote-unquote, the reasoning models, the ones which try to kind of improve the accuracy of planning and reasoning problems. The two things that we look at essentially are the two things we are looking at is one is the test time scaling, which we talked this morning, which basically you let the LLM generate, do more work at the inference time, and then some verifier or some majority vote tries to pick, and that sort of improves the robustness. And actually the test time scaling, you can explain why it works, essentially, because if you have a verifier and if you're generating more solutions and the verifier checks, then you can actually explain why it improves reasoning. The second part, which is the post-training, is a harder thing. All it does is it improves essentially the solution guessing that LLM is doing. And the difference is, I wish I put that slide here, essentially in addition to all the data that standard LLMs have already been trained on, you are now training them with synthetic data and their solutions. So there is a knowledge web on which the standard LLMs have been trained on. And then there are the synthetic data, the reasoning web, where basically for any kind of reasoning problems, they, as the length increases, you have different instances. And so you can generate these solutions, problems and solutions, and then use that to actually train the LLM. That sort of a data is never available in the normal public web that we wrote for ourselves. So you in some sense are creating extra data that corresponds to sort of the reasoning, solve solutions of the reasoning problems, and basically making the LLM, train LLM on that. Okay. So that basically one way you can think of that, the simplest way you can get into this, even though this is actually the current solutions are actually more interesting, is if you think in terms of this LLM modular architecture, imagine after a bunch of generate tests, etc., you finally have a valid solution. You could give this valid solution to the human, whoever is the end user, but you can also store this as synthetic data. That means this particular problem I actually have a solution. So if you solve enough of these, then you have like an extra store of problems and solutions, and then you can then fine-tune your model. You see what I'm saying? This is essentially the simplest way of doing synthetic data. And in this case, actually, the synthetic data again is the solutions are correct for these new instances for which, in fact, original LLM would have given the correct solutions. You have used the LLM itself along with the verifiers to come up with correct solutions, and you are sending it back to the fine-tuning. And the actual post-training approaches, whatever I just said earlier, is one simple post-training approach. Okay. The other one, essentially, here basically you are getting the synthetic data at the inference time, and then after giving it to the end user, you are also trying to keep a copy of it to train every once in a while, extra amount of fine-tuning for that. The normal post-training approaches that currently exist don't wait for the user, don't wait for the end user at all. During the training itself, you basically generate a whole bunch of new problems and try to solve them using, essentially, you can actually say that, you imagine that you're using LLM modulo to generate and test solutions for many, many problems. Okay, and remember the correct solutions can be generated because we have verifiers. This is essentially, verifier in the loop. And so, except that you're doing it during the training, where you can take enough time, extra amount of time to actually solve training, trial problems, and then get more synthetic data and then fine-tune them. The only difference is the fine-tuning. Normally, old fine-tuning used to be just solution, the problem prompt, and the solution, and then you essentially do supervised fine-tuning for that. Now we actually look at one other thing that became kind of popular and people have realized it's useful is problem specification and some derivational trace. Some steps that sort of, the derivational trace semantics are very questionable. We'll talk about in a minute. But what people tend to think is, originally when OpenAI was trying to do this, they would actually have, for reasoning problems, they would have humans give step-by-step solution with the intermediate steps followed by the final answer. And so you have solution, problem prompt, a bunch of intermediate stuff, and then a final solution. And the important thing is that verification is done only for the final solution, not for the intermediate steps. Actually, you could do verification for the intermediate steps in some very special cases. There are things like process reward models, but they have not really taken off. DeepSeek, for example, doesn't use process reward models. It only uses outcome-based verification. So the way you think about it is, essentially, this is actually what's called the RM post training that DeepSeek has made popular. So the LLM is setting itself new extra problems. For each problem, it tries to generate intermediate token trajectories followed by a solution guess. And so these are all the trajectories. So the question, intermediate token, solution 1. Question, intermediate token, solution 2. Question, intermediate token, solution K. Okay? And if you, in fact, turns out that at least one of these solutions are correct according to the verifier. Remember, there is a verifier still in the loop. So it's actually nice to understand this as LLM modulo, except not at the inference time, but during the training time. So you think of it as internal LLM modulo rather than external or inference time LLM modulo. If in fact at least one of these is correct, then that can give some signal to the reinforcement learning algorithm or a learning algorithm, which basically says, try to change the parameters of the LLM such that it produces the success, the trajectories that seem to be ending in the correct solution, and reduce the weight for the ones that are ending in the wrong solution. And you do this for tons and tons of extra problems. That basically sort of changes the parameters of the LLM itself. So that here basically the parameters of the LLM, as you do this fine-tuning, they'll actually both change the way they generate the intermediate tokens and the solution that they would be guessing. And this idea could have been tried long back. And in fact, by the way we actually know this, people were guessing after 01, which was September last year. But O1 did not have a technical report, as many of you know. OpenAI started writing. I mean, OpenAI is really close to AI. I mean, that's kind of an interesting acronym that the company name that they just happen to have from the old days. But they essentially did not write the technical report, and so we had to guess what they might be doing. People basically guessed that something about test time scaling and fine tuning might be there. So I have like my own speculations that I posted at that time that actually I'll talk about it later. But DeepSeek wrote a paper about not only their model, but this is what they're doing. And as I said in the first lecture, it was even considered that the OpenAI guy said, I'm sure you guys will know what we did after Chinese reproduce it, and the Chinese did reproduce it. And what DeepSeek does do is this kind of RL post-training, and now that it's actually become open, people are actually trying to, academics and the research people outside of these big companies can actually try to see which part of this is making anything work and what doesn't work. Okay, and that is how progress is made. And so we will talk about essentially this sort of RL approaches. And you can also, a variation is that just doing supervised fine tuning without doing any RL. In fact, one of the things that I will be mentioning, I know that there have already been RL lectures here, and I will make connection to the specific MDP model that DeepSeek uses, and it turns out it's a very simplified model with significant restrictions, significant simplifications, and partly that has led to its own crazy extra behaviors that RL is incentivized. For example, one of the things we'll see is if you train LLMs this way, then when during the test time, they will, as the amount of training increases, they found that on the average, the number of tokens in the intermediate token strings, I will specifically call them intermediate tokens, people call them thinking traces, chains of thought, reasoning traces, they're all bad anthropomorphizations. I will actually give you some reasons to support that. But these intermediate tokens increase in length as the RL gets trained. And so people started saying, well, that must mean that RL has learned to reason, because more mumbling you do before giving the solution, the more thinking you are doing. This is completely backwards, and we will actually show that you can actually explain this in terms of how the MDP approach is used. It so happens that for the failing traces, for the trajectories that are not ending up in the solution, RL is incentivized to talk longer and longer before giving the solution, because the negative reward can be diluted over a larger number of tokens. And for the positive things, it needs to be shorter. So people actually have seen that these thinking traces, mostly they increase on average, but the increase is coming because of the failing traces, not the successful traces. And but the real reason has nothing to do with thinking. It's just how the RL is incentivized to do the reward propagation. So we talk about all of this. So the other thing we also find out is the question of, is this really even reinforcement learning? I mean, do you need the word reinforcement learning? Reinforcement learning is a very powerful technique, but in fact, the specific kind of models that DeepSeek uses, at least, they are not really, you could actually have done equivalent performance with just supervised fine tuning, incremental supervised fine tuning, and we'll also find that out. Okay, so this is, we believe some of these might be behind O1 too, when O1 came out in September last year. So the question basically is, when that came out, up until then, remember I was showing these pictures of, as new models come, we will check how are they doing in the PlanBench, and they'll all be doing pretty badly on this tree domain in particular, and they were doing slightly better as time went on Locksword sorts of approach domains. So when O1 came, just before that, in August, I was actually at ACL, and I gave a keynote at ACL about planning reasoning models. And then there I used actually a simple example to just show, I mean, I didn't use any of the simple examples here, but a simple example to show, for example, anecdotally that LLMs actually fail to do planning. And one idea is here, basically, this is a impossible to solve problem. And there's no solution to it, but LLMs will actually just try to give a solution. And I pointed that out and said it's a simple error. And when O1 came along, Noam Brown tagged me and said, whatever Rob said, now O1 can solve. So no, it was interesting, and so we started checking how does O1 do on this PlanBench. And one of the funnier things is, as I mentioned in the first lecture, O1 actually was charging an arm and a leg when it started. So we spent like $8,000 to do these experiments. Now you can do it much less because they are reducing the price much more significantly. So this was September 20th, 2024. LLMs still can't rank and LRMs, and the word LRM was made in that paper. So basically we just made up that thing, and then that finally got peer reviewed and appeared in Transactions on Machine Learning. By the time this happened, DeepSeek also came, so we did the evaluation on DeepSeek too. So this paper actually, and the results that I will point out in a minute, contain both the O1 evaluation and the DeepSeek R1 evaluation. Okay, so what did we find? What we found is, so here is a whole bunch of models. This one doesn't have R1, this is only O1 and O1 mini and O1 preview, and a bunch of standard LLMs, GPT-4s and the Claude family, etc., etc. And then we basically looked at the problem complexity in terms of the length of the plan in blocks world. And if you know anything about search, as the length increases, that's like the depth of the search tree, and so the complexity increases exponentially. It's d power d, if you remember from the old days, we had. And so what we find is for the smaller lengths, essentially O1 and O1 preview do much better than the standard models. They start higher up, as you can see, and these guys are actually much lower down. They're actually pretty bad. Especially this one is a mystery blocks world. Remember, the mystery blocks world is our gold standards. That's the one that was doing very badly on. And so mystery blocks, they are all in lower level. O1 actually and O1 preview were doing much better. But then as you increase the length, they fall down. Okay? And this is basically what about 9 months later, Apple paper is actually pointing out to that. In fact, if you increase the length of the problem, if you become more complex, and all these reasoning models are so bad. It's not surprising, and that's basically what we pointed out. And so anyway, so that's the one of the important pieces of results. The other result basically is that, especially that's something, this is actually probably not as relevant now because the costs kept coming down over the time. But at that particular point of time, we could actually talk about the cost to access these models, and obviously the O1 and O1 preview was significantly costlier. So it's like out of pocket cost was much higher to get the same level of accuracy. And the joke that we had was, you can't have AGI because you can't afford AGI, because you need like really, really big, account to keep paying some amount of money. This is more with not just blocks world, mystery blocks world, the randomized mystery blocks world, logistics, mystery logistics, and Sokoban. Remember the Sokoban, which is actually the non-ergodic domain. And you notice that in Sokoban in particular, it's 12.73% for O1 preview, compared to in blocks world 97.8% accuracy. You understand the difference in terms of, ergodic versus non-ergodic words. Okay, so Sokoban is still pretty darn high, cost for any of these reasoning models. And this was at that time itself, in September itself. Okay, we also did some analysis of the kinds of errors that these reasoning models are making on these kinds of planning problems. So in blocks world, of course, 97% of the time they are correct plans. Sometimes at 2% they're inexecutable plans, and then 0.17%, it's executable, but it doesn't actually reach the goal. You can do this kinds of analysis. Sokoban, everything is pretty bad. Valid plans is 12.73%. Most of the time you get invalid plans. The paper also contains an analysis of unsolvable instances. That is, you actually generate instances that don't have plans. And it turns out that actually unsolvable instances are really, really bad for standard LLMs, because they don't think that it's possible to not have. In fact, if you train LLMs to say, I don't know, then most of the time they'll wind up saying, I don't know. So they're actually, in the RLHF training, etc., they're incentivized to say something most of the time. And so unsolvable instances, you wind up actually showing that they do much worse in general. In the case of these reasoning models like O1, Sometimes it will basically agree that unsolvable instance is unsolvable. Sometimes it will actually give a plan and argue with you that it is a correct plan. That even though it cannot be solved, but it will try to give like long amount of arguments saying, this can be a correct plan. So, and so that's when we said basically it's no longer hallucination, it is actually gaslighting. It's trying to tell you that your domain is not what you thought it was, and in fact there is a mystery plan that actually can sort of cut down. Okay, and as I said, cost considerations in general at that time looked like a very significant thing. They're still very significant. In general, you have to understand that online computation, nobody likes it because if you do offline training, it's Sam Altman's problem. If in fact you are paying out of your time or pocket money at the inference time, that actually bites you, and so you are not too happy with that. And in general, cost considerations are likely to change the market, considerations for the use of these kinds of systems. Again, people are cutting down the cost, and the major companies are cutting down the cost for access, but this seemed like very important at the particular time. DeepSeek-R1, that paper also contains DeepSeek-R1 results, but DeepSeek-R1 actually is not as good as O1 Preview and O1, but it was completely competitive, and it was significantly cheaper. In fact, people say competition is good. Competition even from China is good. It turns out, right? Because it's very clear that if there's no DeepSeek-R1 with open models, then, I'm pretty sure Sam Altman would like to charge you as much as he can. If to the extent that that's the monopoly. And the moment DeepSeek-R1 wound up becoming feasible, they basically cut down the prices. Suddenly, magically, the cost became much less because DeepSeek-R1 actually is much, much cheaper. And maybe they had their own, I have no idea what their philosophy was. Maybe somebody was subsidizing their cost and so on, whatever. But whatever it is, as end users, in fact, it turns out that the costs were actually much lower. So basically, you have both the costs as well as, so that's like cost per O1 preview for doing these evaluations was about $42, and cost for doing the same thing on DeepSeek-R1 was $2. Not bad, right? I mean, it was a significant reduction. And then, of course, these guys also reduced after that fact. Okay. Anyway, if you understood these results, 9 months later, essentially, is the Apple paper. That pretty much is pretty obvious that that's exactly what was going to happen with reasoning models. The only difference is, in addition to DeepSeek-R1 and O1, they also considered Claude and Gemini. I don't know whether they considered Gemini or Claude, or Claude reasoning model. In fact, many of the companies started putting out these reasoning models. Most of them, other than DeepSeek-R1, we have no idea what they're doing. Nobody actually explains it. We only know black box evaluations of it. Okay. So the other thing is, where does this? One of the interesting things is we don't actually know what O1 does in terms of whether it only does post-training or it does post-training as well as test time scaling. Okay, so one of the things is that it will take longer before it produces the solution because it's producing a large number of intermediate tokens. But LLMs trained to generate intermediate tokens will produce intermediate tokens until the end of intermediate token result comes, at which point they will start outputting solutions. So that's not actually test time scaling, it's just, because of the post-training, you are biased towards generating longer and longer length intermediate tokens. And people basically have done some various analysis of that and thinking, is the amount of intermediate tokens generated connected in some way to the problem complexity? Once again, as I will point out, it's not all that clear that that's happening. But one interesting thing is, I don't know whether O1 was doing test time scaling itself, but I could do test time scaling on top of O1. In particular, remember I had this, LRM module framework. I can make it large reasoning model instead of large language model as the middle guy, and it then guesses the solution, and then I will still do the verification and check, go back and forth and so on. And one of the interesting things is the MLR paper shows that, and so in this case, essentially you are doing both post-training and inference time test time scaling, right, with the verifier. And basically, we show that with the LRM modulo, so for example,
Sokoban was 12.7%, but with the LRM modulo it goes to 43% accuracy. So you can increase O1's accuracy by doing S-time scaling with LRM modulo in particular. And also with the LRM modulo, you have guarantees. The solutions that are coming out are guaranteed to be correct because the verifiers have checked those. And then if not, it will just keep going back. And so in general, generate test is a pretty dumb idea for search unless you have a good generator. In which case, actually, it can be a pretty efficient idea. And LLMs are reasonable generators, LRMs can be even better generators, but without guarantees. And it is this bank of critiques which is actually standing guard and making sure that things coming out are actually correct. Okay, so that's LRM modulo. And then this is in some sense, as I said, you can think of this as combining test time scaling and post-training. We don't know what O1 did, but R1 does not do this. R1 just basically is an LLM in the inference time. It doesn't do any verification, it doesn't do any test time scaling techniques that I talked about, such as majority voting, etc. None of that. So at least one of the advantages of writing a paper is we know what they did, and so you can falsify. And science goes by falsification, essentially, right? If you never say what you did, then nobody can question what you're doing. So in general, in fact, in those days, again, we actually found that when I say in those days, I mean last year. That's the speed at which we are moving right now. LRM modulo actually can actually be cheaper. LRM modulo on a standard LLM can be cheaper than using O1 directly. Do you understand what I'm saying? LLM modulo on a standard LLM can be cheaper than doing O1, but with higher accuracy. And because O1 was particularly costly at that time. So this is where we are. And what I want to mention the rest of the time right now have is what are some of the things that are basically still completely misunderstood in terms of, or at least we don't understand why they are working. They seem to be working, we don't know exactly why they're working. And so in general, LRMs can be understood, as I said, as incrementally compiling the verifier signal. I will point that out. And then I also point out that the intermediate tokens have been, many people think of them as thinking places and they try to make sense of them. That's a major focus right now, and so we have a couple of papers to point that out. So the first one essentially is you can actually think of what is happening in DeepSeek R1, and again, nobody knows what is happening in anybody else's reasoning models because they don't write papers. Okay, so DeepSeek R1 and the variations of that, and then some of the smaller models that the academia has been publishing, as incrementally compiling the verifier signal into the generator. Okay, so it's like the generator was, if it's a normal LLM, it will be generating large number of choices and some of them are right. And as you do this post-training, you increase the density of the correct guesses, sort of statistically speaking. And the way to understand this is essentially the DeepSeek R1. In fact, the RL's post-training could have been done long back. The advantage, the reason it didn't work before and it started working more recently, interestingly, is because the base models, first of all, have been trained on synthetic data already, without even before the advent of reasoning models. And they also have been trained with some sort of the derivational traces, so that you can then prompt them to give intermediate tokens followed by the solution. And once you have that ability, then essentially the underlying LLM, the base LLM, might have, let's say, pass set 15 accuracy. That's reasonable. That means if you do 15 guesses, and if any one of those guesses are correct, I'll give you a point. And then if you are about 90% accurate that way, that means 90% of the time, one of your 15 guesses for your problem is correct. What you really want is pass set 1 accuracy, not pass set 15 or pass set 64 accuracy. What basically happens in this training is you start with something that has reasonable pass set 15 accuracy on a small distribution of problems, and then with this post-training, the RL post-training, you are essentially pushing that from pass set 15 to pass set 1. In doing so, it's effectively doing better on even the larger instances. And so now you can redo this whole thing with this changed LLM, but now with a longer horizon problems, longer inference horizon problems. And that's pretty much what happens if you think in terms of the way SFT, RL tuning, and the distillation that happens in DeepSeek R1. It's actually kind of slowly building itself to be more and more correct for longer and longer inference horizon instances. This is actually unsatisfactory because it will never really learn the algorithm for large data concatenation, which is a one-line algorithm. Instead, it becomes better and better for, okay, I'm quite good for 10-word instances. Now after a while, I'm quite good for 20-word instances too. Now after a while, I'm quite good for 30-word instances too. Do you see what I'm saying? So it's not actually learning the underlying algorithm. But the advantage of this is it's not trying to just learn a single algorithm. It's essentially learning, whatever the data that's been trained on. Some of those data have been, that may be a mixture of problems coming from very different algorithms. And so that's sort of the advantage that it has. And so that's one thing to understand, that really the improvement is verifier signal slowly seeping into the generation. That's currently where we are at. And if you, as I sort of showed this fast yesterday, that if you think in terms of, let's say, multiplication accuracy as these reasoning models improve, you will realize that it's becoming more and better for the larger and larger multiplications. Now, if you write this for a cheapo calculator, it will be completely green. Because cheapo calculators are good for every possible multiplication. But if you want to do multiplication with O1 and O3, after paying money, you still are actually pretty bad. And it's just that you're becoming better and better with the green. And this one actually, their research, I think, showing that transformers, especially empty transformers trained to do multiplication, wind up improving their accuracy, incrementally, piece by piece by piece. They never learn the multiplication algorithm. This is, a paper by the research group. The next part that I want to talk about is the anthropomorphization of intermediate tokens. That's actually a pretty unfortunate issue right now. So basically, people, and DeepSeek R1 played a big part in this too. Actually, O1 never showed the intermediate tokens, so we have no idea what nonsense was there in the intermediate tokens. They said it's commercial secret, and so if you actually try to figure out what the intermediate tokens are, then you can see your account. DeepSeek R1 thankfully gave everything out, but then they started also saying, now this shows that it is thinking. And one of the interesting things, if you remember, R10, which just does direct RL fine-tuning, combines English and Chinese. And apparently that's not a good way to think. I don't know, please don't misunderstand me. It's a DeepSeek R1 saying you should mix languages in your head. And so they basically generated humongous amount of additional human annotated data, which is only English intermediate tokens, and then retrained with that. And they reduced the accuracy, but at least it's all in English. Somehow English is connected to reasoning apparently for R1. It turns out that's all nonsense. I'm showing you in a minute. Yes?
Sorry, I may have missed but what changed in the training of the models that made them produce the intermediate tokens?
So basically, there are two different things. First of all, you can always tell even a simple LLM from the GPT-3 era, saying, here is a problem, tell me about how you are solving before giving the solution. And it put some random amount of stuff in the middle before giving the solution. What changed additionally is, over the period of time, more and more of data with these intermediate traces has become part of the training data. So that V3, which is the base model for R1, already gives intermediate tokens followed by the solution. And then it's now, RL is really just selecting among those trajectories, sort of, okay? So the question is, there is expectation that the intermediate tokens of LLMs are reasoning traces. There is little reason to believe this, but it's hard to evaluate formally. And the problem basically is, this, by the way, is the intermediate tokens, I call them mumblings, from DeepSeek R1 solving a mystery domain. Okay? Notice there's no Chinese in it, so it must be thinking. It's all completely English. Okay? But it's page 1, page 2, page 3, page 4, page 5, page 6, and finally there's a solution. Did you guys read the whole thing and figure out whether it's thinking or not? Of course none of us did. It all looks English, right? And so what you wind up basically doing is, do you see the animals in this? This is a Rorschach ink blot test. People basically look at these and say, these are symmetric things and say, oh, there is a animal, there is a bird flying, there is a tiger about to pounce on something, etc. We basically look for patterns like this. And so if you look at this English, it is paragraphs, and it says some pseudo-English that the sentences that seem to make sense. But the overall thing is not actually going anywhere, and you can't actually check. How do you simulate the reasoning trace to see if it actually reached the solution? You can't. So you can't actually question. But although, as I said, DeepSeek actually wrote like a whole big thing about the aha moment in the paper. In fact, at some point of time, the model said aha. Hey, your data said aha. And LLMs copy style. So if you said aha, your LLM will also say aha once in a while. And if you're only picking the piece by piece, then you'll wind up getting confused. Okay. So what we did, one of the things that I'm actually pretty proud of, is we looked at the cases where the intermediate traces can actually be simulated for their correctness. And when that happens if you actually, so that's this paper, Beyond Semantics, it's available, it's just preprint still. And what we did was we took, basically maze following path planning problems, and we generated multiple random mazes with very different distributions so that you can actually do both in distribution versus order distribution evaluation. And then for each of them, we are solving these mazes using A-star search. A-star search essentially modifies two different data structures, open list and closed list. So you essentially take all the modifications that it does, that's the intermediate tokens followed by the solution. In fact, there's work like search farmer and scheme of search, which actually show that if you do train the LLM not just with problem and the solution, but problem, intermediate tokens and solution this way, its performance improves. The question is, they check, when they say performance, they check the end accuracy. Nobody is checking these 30 pages of doubling that we produce because nobody knows how to check. In our case, we can check because these are actually A-star manipulations of data structures. So I can have an A-star simulator that takes you at your face value when you provide an intermediate trace before your solution and check whether or not that actually is correct and is leading to the solution. And so we can also look at the kinds of errors that might be there. And this thing is not meant for humans, but it actually makes sense with the A-star search completely. And this is the confusion matrix. This is basically showing if you train an empty transformer with Wilson generated puzzles, and then you test it on Wilson generated puzzles or Kruskal generated puzzles or the different distributions. You will notice that the diagonal entries are the good ones. That means the solution is correct, the trace is correct. Or the solution is wrong, the trace is wrong. But the off-diagonal entries, they should be zero. The fact that they are not zero tells you that there is no direct correlation, there is no causation between the trace correctness, the trace validity, and the solution. Okay? Now you see this, then we ask the next question, does correctness even matter? So one way of checking this is we took the traces for problem 1 and swapped it with the trace for problem 2. So these are wrong traces but correct solutions. Okay? And you train the transformer that way. And then you check the accuracy, and one of the things that's mind blowing is it actually improves performance. So in the case of this particular case, 2.5% to 26%, notice that the trace, all basically these badly trained models, the traces they output at the inference time are completely invalid. But their solutions are actually more accurate, more of the time. And everybody is only checking the solution accuracy. But they are making all these anthropomorphizations about the intermediate tokens and what they might be meaning. So that is the thing that we want to point out. In fact, we did this experiment not just on the puzzles, but question answering kind of a problem, where it's like a question which can be split into sub parts, and then you can make an automated way of generating intermediate tokens followed by the final solution. And we basically did these experiments on that particular data too, and we found more or less similar results, that essentially trace validity is not giving solution accuracy and vice versa. This is important for you to understand. And so we basically have the same sort of confusion matrices there. So why should you care that the trace has actually no connection to the solution accuracy? It looks English, why can't we think it is thinking? The problem basically is you are going to have to depend on these models, solutions, when you don't know the correct solution yourself, in the worst case. And if you wind up believing the solution more because of some gobbledygook intermediate trace that you actually didn't check, that's sort of a direct attack on our cognitive flaw. I mean, I give this example that imagine, I may have said this in the first day, that imagine I have a question for which I don't know the answer. I take two people in the first and second rows, and I give them both a piece of paper with the question and ask, what do you think is the answer? One person writes just the answer, nothing else. The other person writes a different answer, but a whole bunch of calculations, integration, differentiation, multiplication, all that stuff. I'm more likely to believe the second person. That's just a cognitive flaw that we have. And we should be careful about that. It doesn't make any sense to say intermediate tokens are reasoning traces when they actually are not. Okay? So, and it actually becomes, and more importantly, it becomes an albatross on the post-training. Albatross basically is like an albatross around the neck. Just to actually generate these reasoning traces that are in English, R1 took a hit. R10 had higher accuracy, but just so that they can have the intermediate tokens in this mind-numbing English, they took a hit on the accuracy. And in fact, that's what I showed you, that if you actually change the correctness, if you actually train the correct traces, you can actually be improving accuracy. So if all you care about is improving the optimality of the final solution, that work directly on that rather than working on trying to make some training statements about the intermediate tokens. That was the point. The last point I want to make is the RL talk of the deep sea carbon again has led to a bit of a specific kind of a carbon industry. In particular, as I said, normal MDPs involve an environment which has a state, agent takes an action, the environment transitions to a new state, and so on and so forth. In this particular MDP that deep sea carbon uses, essentially everything is just available. So context window becomes the state, and the next action you take becomes part of the context window. The state is basically, let's say you start with token A1, and then you do action A2, then now the context window is A1, A2, then you do action A3, then the context window is A1, A2, A3, and the transition is basically deterministic. And worse yet, you get the reward at the very end of the trajectory if the solution is correct. And this reward, normally RL is used to do the creative assignment. So if you're doing RL for AlphaGo, right, if you do a bunch of moves and then you finally won the game, it's the RL slowly figures out which were the important moves, which were not the important moves. You short circuit that whole problem in this case, in the way the reward metric is set up in R1, by directly giving every token in the intermediate token list equal amount of reward, 1 by n. And weird thing is that if you do that 1 by n reward, then you are incentivizing RL to give longer and longer traces when they're actually going to run solutions. Do you see what I'm saying? And so that can be seen here that they normally just look at the average length of the intermediate tokens over both correct and incorrect traces. But if you split them into correct traces and incorrect traces, the intermediate token length doesn't increase. On the other hand, for the incorrect traces, it keeps increasing. So if you take the average, it increases. And the reason this is happening is because the negative reward can be diluted over longer traces. That's what is explained in the paper. And so, in fact, as you see, basically the average at any given point depends on both what is happening at the correct traces and incorrect traces. So again, a misunderstanding that gives wrong incentives to RL, and then there's a whole bunch of pointing about, well, this must mean RL is increasing its thinking because the traces have become longer and longer. There are other kinds of variations. So one of the things is you can get the same level of performance that is shown in the paper without RL. They're just doing incremental SFT for that particular setup. And so it's not that RL is not a great technique, but it's not really doing anything, not as much as you might be thinking. So one other mind-blowing thing is there's actually a paper that came out last week or 2 weeks back, basically doing the same kind of thing that we did with beyond semantics, except for the RL reward. They actually trained post-trade RL with completely wrong rewards. When the solution is wrong, you get the points, and if the solution is right, you get 0 reward. You would think that should definitely reduce accuracy, right? It actually increased accuracy. Okay, and so much so that now it turned out that people have figured out that, again, there's a nice China connection. A Quen model basically will start improving irrespective of what you do. Okay, so Quen model has this ability to start producing code, and normally it doesn't. But if you do any kind of post-training, in the right way or the wrong way according to you, it winds up producing more correct answers. So you get to write papers. There are at least 25 papers written already on this stuff. So much so that now, besides the joke that I wrote, that basically all the great head-spinning number of RL/LLM results really depend on the math data being used on Quen models. They don't work for any other models. The point I'm trying to bring up here is you need to know what you understand and what you don't understand, so that the parts that you don't understand, you can actually work on. And that's part of what we're going to do here. On the whole, we basically wrote this question paper, kind of taking all these points to say, stop anthropomorphizing intermediate tokens. It's not actually needed. And in fact, there can be better ways of doing RL that maybe in fact Google is doing. I have no idea. In fact, they did AlphaGo, and you can actually in the TMLR paper, I basically have a speculation as to how you can do a 2 LLM model for RL, where one LLM only generates prompts that the base LLM would be responding to, and you only learn the policy for the prompt generator. And it turns out that that's actually a different kind of an approach, and that can have very different properties. We don't right now know, because we don't know if Google is doing it, and we certainly know that that's not what RL is doing. So that's a speculation that I posted at one point of time in September, but it's also part of the TMLR paper. So, summary, I kind of, over the last 3 lectures, I sort of tried to get you to understand that LLMs trained just on the knowledge web, the web corpora, were known to have severe limitations on planning and reasoning tasks. They can still be used as generators in a generate test cycle with the LLM modular approach. The improved reasoning abilities can be compiled into a base generator with either SFT or RL. That's what is happening in the post-training. The resulting LRMs still have no correctness guarantees but are better generators. So if you actually put like LLM modular on top of it with test time scaling, you can further improve its accuracy. And then the last part I basically was trying to tell you that there is a huge amount of anthropomorphization. There was a lot of anthropomorphization with the standard LLMs, the chains and the thoughts and the thinking and all that stuff. And we wrote a bunch of papers saying, calling off on that. But there is still a bunch of new kind of anthropomorphization. It's the point the reason we hate anthropomorphization is that they give you illusion of understanding, not real understanding. And you then have to write these papers to actually figure out what is actually working. Okay, if these are already, these 3 lectures are the latest understanding I have, so in fact, those are the ones that I recorded for you. But I have the older ML Street Talk stuff that will be more general about LLMs and also LRMs that you might be interested in. And there is an ICML tutorial that's 1 year old, so it doesn't have anything about LRMs, but it has a lot about LLMs, a little bit more. And this is the ACL talk. As I said, if you want to just remember anything what I said, just look at these 2 papers, and it sort of gives you an abstract of what I was saying. The details are, of course, the papers. Again, as I said, those people, other than the guy here, the rest of them are the ones who are actually doing the work. I get to come to River del Sol and enjoy the ocean while they still continue working on new papers. And I stop here. Thank you for your patience. And I will be here for the rest of the day today. I may not be here tomorrow, so if you have questions, please ask me. And thank you. I was trying to give my 10 lecture.